the symmetry, we learned point groups and so on, and we showed how we could do three-dimensional integrals and learn if they're zero or non-zero. But now in Excel, we'll do one-dimensional integrals and differentials using Excel. So these are numerical approaches to the Schrodinger equation and the transition dipole moment integrals. Now, why would we use these methods? Well, for one thing, Excel is very visual. You can plot the wave functions. You know, you're seeing the wave function of sine n pi x over L plus, pi over 2 or whatever it was. You might have a visual of a sine function in there and so on, but Excel, you can plot them all out. And it's just really nice, okay? And so Dirac told us, we need to have approximate solutions that are easily implemented. And so that's what we're doing. So this is next week's lab. So this video will be important for you for being successful next week. So next week, we're going to have a spreadsheet. The whole lab takes place in a single workbook. And it walks you through. There's like 4 panels. So the first panel is on the wave functions. Okay, and so we have this area. So you're going to go through and you're going to plot the wave functions. So the Excel sheet you get is empty right here. Okay, and so you get to practice your anchoring and all of that stuff. So you'll type in the square root of, L2 over L times the sine function, an open parenthesis, and then you need the quantum number. So then you'll go up to the quantum number and you'll hit anchor, okay? And then you do times pi, and in Excel, you don't type in 3.14. There's a function that returns pi out to a gazillion digits. So that's pi, open close parenthesis. It doesn't take any arguments. It just returns pi. It's like calling a function. Go get me pi, and Excel says, here it is. And then times in pi x times the x. Over here, you want to anchor just the column, okay? So that when you copy it over 1, it will anchor the column. And then for n, you just anchor the row. So when you copy it over, it moves the column, but doesn't move the row when you copy it down. So you can anchor all those different things. And then paste it down, and you have 2 wave functions. Now you can play around with the quantum states, and you can see the wave functions change. So if you plot those, that's what we have up here. I've got quantum state 2 here. You can see it, the blue one. And quantum state 3, you can see the red one. Now, so that we can keep it all on one page, I only have 10 rows. Okay? So you see it's kind of choppy. And there's some questions related to that. How many nodes do we have? Yeah, so for wave function 2, we have 1, and for wave function 3, we have 2 nodes. Really, the quantum number tells you how many lobes you have, how many non-zero parts. Okay, and so we see there's 2 lobes for quantum state 2 and 3 lobes for quantum state 3. You can't have 3 lobes without 2 nodes where they switch sign. You can think of it too as the number of the quantum state minus 1. That's the number of nodes you have for a particle in a box. Okay, so what if we were to? We see that we have a point every there's 10 points across our curve. What if we had quantum state 10? Then the data points would be on all of the nodes, and our wave function would look like it went away. And that's the downside of numerical analysis, is that it depends on the number of rows you have. Your results could be in error. Okay, so we'll see that in this spreadsheet. That'll be like part of the exercise that you'll analyze in the discussion question. Okay, so we have that wave function. Then we just have this first wave function here, this column here, squared, just to show that all of the values are positive. And so we plot that here in blue. We squared it. Okay, so there's the wave function squared. Then we have wave function first column times second column. Okay, and that's plotted here, the red. Okay, now if we integrated this blue one over all space, we take the area under this curve. What do you think we get? Because this is a normalized wave function. We're looking at wave function squared. What do you think we get when we integrate that from the left to the right? 1. We get 1 because it's a wave function times itself. That's the probability distribution. And then what if we integrate this red one? Can you see that we have some positive pieces and some negative pieces? and the positive and the negatives would cancel out. So if we integrate the result of wave function 1 times 2, or the first one times the second one, we would end up with 0. And so we see that it's orthogonal. So we can show normality and orthogonality in this spreadsheet very easily, just plotting our little functions. So this is a numerical analysis. And we're doing integration. And we don't have to know any trig substitutions. We don't have to think about, any of these integral properties. The integral of sine is minus cosine or whatever. Okay, so that's pretty cool, I think. Hopefully you'll enjoy this lab. Then we have, just to show, like we have the sum of this column times delta x, and we get 1. We have the sum of this column, which was wave function here times that one. I don't want to say 1 and 2 because this is really 2 and 3. Okay, so we have the sum of this column, and we see 0. Now, I show you a couple of different ways to do that integration. So if it seems redundant, it is. I just wanted to show you, we could do it for the slow way, where we squared this column, or we took these two columns times each other, and then we just sum those columns times delta x, or we could do that all in one shot with the sum product. And so this is sum product, this formula here, and in the parentheses, you just put this column, comma, and this column again. And so it's taking those two arrays, multiplying them by each other, and adding up the result. So you can do it all in one shot right here, or you can do it using matrices. And so this is showing you how to do the matrix one. And so there are little formulas up there in that box. So all you're going to do next week is get that spreadsheet, download it off of Blackboard, and then work your way through panels at a time. So this first panel is all about the wave functions, all about orthonormality. You can see the Kronecker delta, right? The diagonals are 1 and the off diagonals are 0. Okay. And so this is showing an orthogonal and normal normality of the wave functions. Now you can have some fun with it too. You could pick, instead of like 2 and 3, you could do like 1 and 3. You could do all kinds of things with this. Have fun with it. Okay. So that's the first panel. So this arrays are just, groups of numbers. This is a little bit of a review from the Excel bootcamp. This is where you'll utilize some of that stuff. And we can do matrix multiplication, and that gives us numerical integration. So any row or column or block of numbers is an array. Okay. And so these wave function columns, those would be arrays of numbers. Okay. And so we refer to matrices as row by column. And so you may hear me sometimes talk about a single column of data and still call it a matrix. Okay. Well, that's just, let's say we have 10 rows by 1 column. It's a 10 by 1 matrix. Some people would, just because it's 1 column, call it a vector. That works as well. Okay. Or an array. So all 3 of those terms are essentially the same. It just might have some slight difference in nuance, like a vector or an array can be single column. Matrix typically has more than 1 column. And then if we transpose something, we're taking it from a row and making it a column, or taking it from a column and making it a row. We're really flipping it on the diagonal, which by definition has to contain the very first cell. Okay. So if we transpose the column, it becomes a row. If we transpose a row, it becomes a column. So this is important because of the matrix multiplication. So if we transpose a matrix that's not just a single column or single row, you can still see how it rotates around that diagonal. So look where C went. It's down here. It's like 2 off the diagonal. Now it's 2 off the diagonal, but horizontally. A and E are in the same spot. So everything just kind of pivots around that diagonal. So in Excel, this is how you do it. It's the transpose array. Now the trick is, in Excel, let's say I have, I want to transpose this data, and this might be a column of numbers, and for some reason you want to make it into a table that's horizontal instead of vertical. You could use transpose to do that, but you have to select the whole area first. So you got to know what the result is going to be. That's why it's important to know these facts. So if I take that data that's a 2-column set of data that's 3 rows down, I got to select 2 rows and go 3 columns over. So I select that whole area, and then I type in equals transpose, and when I open parenthesis here, I'm going to go with the mouse and I'm going to select this whole area here, what I'm transposing. And then close parenthesis, and then I hit the Control Shift Enter to make an array formula go. And what that Control Shift Enter does is then it kind of copies that formula into all 6 of these spots and generates the data. So array multiplication. So in this case, 1, 2, 3 times ABC, you see that this first column is multiplied by the first row, and it goes here, and it's added to this second value, and it's added to this third value. So this is an integration right here. And if we took that and we multiplied by dx, oh, wait, what am I doing? Delta D here. Multiplied by dx, then we would have integration. So in Excel, if we did sum product array 1 times array 2 times delta x, that would be our integration. But the problem is there are certain rules in terms of matrix multiplication. So let me jump ahead to that. Here's the matrix multiplication rule. So we list our matrices row by column, so it's always row first, then column. And the columns and the rows have to match. So these pieces right here have to match because of the way matrix multiplication takes place. So if we have a 2 by 3, that's compatible with a 3 by 2, and it will result in a 2 by 2. So you have to know this because you've got to select a 2 by 2 matrix to do your array formula. So that's why these rules are something that Excel's not going to tell you. You have to know how to do matrix multiplication by hand, even if you're not going to do it by hand. You got to know what the result is going to be, so that when you select the resulting cells and you type in, the transpose and mmult and so on, then you won't throw an error. So this is the formula here. You have mmult in your 2 arrays or matrices that you're going to multiply, and then you do the Control Shift Enter. So this is how we do our wave functions. So we're going to transpose those wave functions. So we would type in that formula equals mmult. No, first we would select the result. Okay, so what have I got? I've got these 2 columns of data. When I transpose one of them, I have a 2 by 11 matrix, and then I multiply by the original 11 by 2 matrix. And so the 11s are compatible for multiplication. Those are the inner pieces. And so I've got to select a 2 by 2 matrix. Okay. And so what that is that's every column times every other column added together. So it's the integral of every wave function times every other wave function. We only have 2, but this is what we get. But I can't just select the column and do, psi, comma, psi, because then it would be a 11 by 2. It would be vertical like this. And this top row can't be multiplied by this whole 11 row series. So I've got to transpose it first. So I get this is now a row times this column added together to give me this first number. And then this whole first row times this second column added together gives me the second number. Then the second row times the first column gives me the second row first column number. And then the second row times the second column gives me the second row second column number. Okay. So that's how matrix multiplication takes place. You've got to know how to do it so that you select the correct number of cells. So we would select those 2 by 2 matrix and type in equals M mult. We open parenthesis, type in transpose, open parenthesis, then we go select those cell values, close parenthesis, comma, and then we go select those cell values again, close parenthesis. Don't forget to do times delta x, so you find the delta x value somewhere on the spreadsheet, wherever it is. There is one, so go find that, delta x. And then you hit Control Shift Enter, and it'll do the matrix. And you've done 4 integrals like that with Control Shift Enter. So that's fantastic. And you get this, the integral of wave function 1 times 1, 1 times 2, 2 times 1, and 2 times 2. Okay. And we see that orthonormality, the Kronecker delta, where it's equal to 1 when n prime equals n, and it's equal to 0 when n prime doesn't equal n. Any questions thus far? Okay, then we go to the next panel. The next panel is solving for the energies of these quantized states. Now, I've expanded this to 14 cell values, but I've got my box here. It starts at 0, goes to 14, so really it's 15. And I've got the wave function in here. Okay, no, this is x. And so here's my wave functions. And I've got this box pointed out here, okay? We need more values on the outside of our box because when we're taking the derivatives, we need to do what's called centered derivatives. We'll talk about that more later. But what this does is it keeps our wave functions from shifting when we do differentiation. If you think about doing the slope, it's rise over run. It's the change in y over change in x. So if I'm standing at point number 1 and I want to calculate the slope, when I do the change in y, I'm using the y for point number 2 and subtracting the value at point number 1. And I'm dividing that by x at point number 2 and difference with x at point number 1. So I've taken information in front of me, and where do I plot it? I'm plotting it here, so I'm sort of pulling information back. Well, that's going to be a problem. If we pull this curve back, it's not going to it's not going to change sign right at 0. It's going to change the symmetry of the function if I do what's called forward derivatives. If I use the next point and then I'll plot it here. So I'm using the forward slope, and the forward slope may not be 0. So let's look at our let's look at this function right here. If I use the forward slope, look, it's a positive slope. Do you see that? If I use the slope from behind, if I use the previous data points, then the previous slope is negative. And that's not correct either. How do I get a slope of 0 right here? Because clearly it's turning around. The slope of this curve at that point is 0. The way to do that is I take the forward y value and the backwards, the y value before me, and take that difference. And then I take the x value in front of me and the x value behind me, which is 2 delta x's, and I put that in the denominator. And so now I get the accurate slope centered right here. So what's called centered derivative. Well, that requires a couple of extra points outside the box region. And so this one, notice we have this is little 2 increments of x beyond the left side of the box. And when we do those centered derivatives, I lose that row. I can't actually calculate this one because there's no data right here. Okay, so we lose a row every time we take a derivative. And so for the first derivative, I only have 1 data point outside the box. And for the second derivative, I don't have any data points outside the box. This will all be shown right here in this formula. So it's all in the spreadsheet. So we expand the x-axis, and we take the first derivative, and we take the second derivative. And so now we have the wave function here, and we have the second derivative of the wave function here. And so when we take the Schrodinger equation, we've taken the second derivative of the wave function, we left multiply by the wave function, multiply by delta x, and add them all together, and we end up with the energies. And so here's our energies for these two quantum states, number 2 and number 3. So we have this energy here, we have that energy there. They come along the diagonals. We could calculate this also with the sum product. And so I have a little table here. I've got the numerical energies, and I've got the analytical energies. So the analytical energies just use that energy equation that we solved with the analytical method. That's an exact solution. So that's our accepted values or our literature values, the analytical, and that's one of my discussion questions. So you got that one right if you can remember this. Okay. The analytical energies are our true values. Okay. It's the numerical ones that are approximate. And we can calculate the error. Here, it says my ground state, or n equals 2, the energy for n equals 2 is 12% low. And the energy for n equals 3 is 26% low. So that's not so great. And the reason it's not so great is we only have 10, we've taken our box and divided it into 10 units. What are we doing when we integrate? Well, think about it. We're taking the y, okay, which is this point right here, and multiplying it by delta x. So we're getting this rectangle, right? It's the area of a rectangle. And then we're taking the next one, and we're adding it to the next one, which is this rectangle here. And you see these triangles here?